Hi, everyone. Welcome to today's webinar in the CERDP and ESTCP webinar series. My name is Jennifer Nyman. I'm with Geosyntec Consultants and the coordinator of the webinar series on behalf of CERDP and ESTCP, and I will be facilitating today's call. The webinar today will consist of a brief overview of CERDP and ESTCP by Dr. Kurt Preston, followed by a list of upcoming webinars in the series. After the opening remarks, we'll transition to the technical portion of the webinar, and today's event features a presentation on Department of Defense research on informed stormwater management. Today we have two speakers from the U.S. Army Engineer Research and Development Center. First, Dr. Billy Johnson will present on linked watershed riverine modeling systems for DoD installations, and his presentation will be followed by a question and answer session. Then Ms. Heidi Howard will present on optimization of a stormwater modeling approach, and her presentation will also be followed with a Q&A session. We will conclude the webinar today with a question and answer session with both speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box that should appear on your screen. You do not need to wait until the Q&A periods to submit your questions. And in fact, we encourage you to submit questions in advance of those sessions. On this slide, we've provided a few suggestions in case you experience difficulties with the broadcast audio. If you are accessing the audio through your computer, please click on the arrow next to the Join Audio button and select Test Speaker and Microphone and follow the steps as they pop up on your screen. If you continue to experience difficulties, please do call into the conference line. You can also, if you have any difficulties, submit a comment to our organizers by using the chat box, which should also appear on your screen if you move your mouse slightly. So please use the chat box for any technical difficulties and the Q&A box if you have any questions for our speakers. With that, I would like to introduce Dr. Kurt Preston, who is the CERDP Program Manager for Resource Conservation and Resiliency. Dr. Preston has tracked his career between civilian university and military positions. Prior to his current position with CERDP, he was a faculty member and research administrator at the University of Nebraska-Lincoln, where he led faculty development efforts to improve research competitiveness. In that position, he also worked with technology transfer personnel, academic departments, and colleges to build university research capability. In addition, Dr. Preston has served as a member of Chief of the Army Corps of Engineers Environmental Advisory Board. Kurt?
Thank you, Jennifer. I'm happy to welcome everyone to today's CERDP and ESTCP webinar. CERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the Department of Defense, the Department of Energy, and the EPA. CERDP's mission is to identify and address high priority environmental science and technology opportunities that focus on DoD requirements. CERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program, in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERDP and ESTCP are complementary programs, with much of CERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scales although occasionally supporting lab efforts are conducted. There are 4 areas in CERDIP and 5 in ESTCP. The Installation, Energy, and Water program is only found in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapon Systems and Platforms, are CERDIP and ESTC programs managed jointly by a designated program manager. Our webinar today is focused on research and demonstrations that were conducted under the Resource Conservation and Resiliency program area, which has essentially 3 main areas of research: natural resources, resiliency, and wildland fire. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. We have 2 remaining webinars in 2018, and we'll be opening registration for 2019 webinars soon. You can find more information about upcoming webinars at this link. Registration is now live for webinars through the end of the year. I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would appreciate it if you could take a moment at the end of the webinar to complete the survey that will pop up on your screen at the end of the webcast. Now I am pleased to announce that the CERDIP ESTCP Symposium will be held for the 2nd year in a row this upcoming November, this very month, in Washington, D.C. The 3-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is available on the CERDIP and ESTCP websites. And I hope you enjoy the webinar today.
Wonderful. Thank you, Kirk. And now it's my pleasure to introduce Dr. Billy Johnson. Dr. Johnson serves as a focus area manager and senior research team leader for the Environmental Laboratory at the U.S. Army Engineer Research and Development Center. He leads research and development activities involving the creation of the nutrient submodel within the Ecosystem Management and Restoration Research Program, and the creation of the contaminant simulation model within the Environmental Qualities Technology Research Program. These water quality modules have been integrated with multiple U.S. Army Corps of Engineers watershed and surface water modeling systems. Dr. Johnson has authored over 40 technical reports, book chapters, journal articles, and other publications detailing his research and development efforts. He has a doctoral degree in civil engineering from Colorado State University. Billy?
All right, thanks. All right, I appreciate the opportunity to talk to everybody today. What I'm going to talk about is a demonstration validation study that we've been doing for linked watershed riverine modeling system for DoD installations. And so the agenda, the talking points today, I'll talk a little bit about the project objectives and the approach that we took, some of the water quality simulation modules that we've been developing at the ERDC, the Engineer Research and Development Center in Vicksburg, Mississippi. Also talk about the watershed and the riverine models that we used in terms of doing the linked approach. Talk about the demonstration sites that we picked and why we picked those sites and the results that came from those, and some of the things that we were trying to achieve in terms of looking at different military installation issues. And then talk about some of the benefits to DoD for implementing a linked system like this, and then just summary and conclusions of what we've found as we've gone through the demonstration study. So in terms of the project objectives, we wanted to validate, and we selected the HSPF hydrologic simulation program, Fortran watershed model, and then for the watershed part, and then the HEC-RAS, excuse me, river analysis system it has been developed by the Corps of Engineers Hydrologic Engineering Center for the linked system. Part of the reason for selecting these two models is just sort of the wide user community and sort of the acceptance by the user community for these two models. We want to assess outcomes resulting from various military activities, and take a look at how and sort of validate the support of this integrated modeling system for installation sustainability. Some of the things that we want to look at in terms of informing watershed management is looking at water, from the standpoint of water quantity and so forth, looking at water quality issues, looking at contaminants, and then also looking at land use impact. So, as the military does things across the landscape, how does that impact some of these other things, and what can we do to try to maybe mitigate some of those impacts? Also, some of the other areas that, a system like this, or what we want to do is demonstrate that a system like this could be used across different climate zones. So when we look at our demonstration sites, you should see that, we tried to pick sites across the U.S. to demonstrate that the same system could work in various climate regions. So the approach we took, excuse me. So HSPF has been around for many years. It looks at watershed processes. It looks at hydrologic processes and in the sense of the channel routings and so forth. Looked at soil erosion, and also looked at point and non-point source pollution. So from the standpoint of the hydrologic cycle, it basically encompasses a lot of the processes that we were wanting from the watershed water quality standpoint. The HEC-RAS model has a long history in terms of water quantity and sediment modeling. Excuse me. What we've been doing here recently is working with HEC to integrate some of our water quality modules in the nutrient simulation module, as well as the CTTF, which is the contaminant transport transformation fate module. And I should make a note that has since been renamed to the contaminant simulation module since in more recent times. But so we've done a tight coupling with HEC-RAS, and part of this demonstration was to kind of show that HEC-RAS with these more advanced water quality and contaminant routines could produce sufficient results for making installation decisions. And we had a loose coupling between HSPF and HEC-RAS in terms of just taking information from HSPF and then inputting that information as boundary conditions into the HEC-RAS model. When I talk about tightly coupled, what I'm basically saying is that the NSM, for those that are developers, they were developed as dynamic linked libraries that are linked at the compile stage. So when you run HEC-RAS, you have these submodules that have basically been compiled within the model. You're not really running NSM and CSM or CTT and F separately. And then from there, once we've kind of calibrated and validated the linked system, we want to see if there are various management questions that the installations have, can we use the system to try to answer some of those management decisions. So we'll talk a little bit about that as we move forward too. I just wanted to note that we have a number of, and I'll talk a little bit about NSM and CSM here in a minute, but we have other water quality modules that we've been integrating with various modeling systems as well. So we have a water temperature model, we have a general constituent model, a solid simulation module, and then we've also been more recently working with the Bureau of Reclamation on a mercury simulation module. In terms of NSM, we can look at some of the things that we account for is benthic and floating algae. We also have a full phosphorus, nitrogen, and carbon cycles accounted for within the system. We can look at CBOD or compute SOD. Some of the processes we have are hydrolysis, mineralization, respiration, photosynthesis, and compute dissolved oxygen and so forth. So pretty much the full water quality nutrient cycling we account for. In Tier 1, we can basically look at a reduced, I guess, state variable set. As we get into Tier 2, we add more state variables and more processes. We can look at in terms of bed sediments, we can look at, just fluxes in and out of the bed sediments, or we've also developed the sediment diagenesis module. So in areas where, maybe you need to, do more detailed computations within the bed sediments themselves, we've actually got sediment diagenesis incorporated into the water quality modules here. In terms of contaminant simulation module, we basically account for chemicals and metals with this. Primarily, it was initially developed for military munitions, but it's developed in such a way that if you know something about the various contaminants, then it doesn't necessarily have to be, a military type contaminant. It could be some sort of industrial contaminant or some other type thing. So it's fairly generic in the way that we can model chemicals and metals. It does a 4-phase partitioning. We can look at a solid particle. So if you have, let's say, a solid metal that's going to be moving with the sediments and it may dissolve into the water column, we can do that. We can look at it in dissolved phase. We can look at it sorbed to dissolved organic carbon, as well as sorbed to sediments as well. So fairly I guess sophisticated partitioning there. We can look at fluxes in and out of the water column and the sediment layer. So you can potentially look at how different say like the sediment at sometimes may serve as a sink for contaminants, and then in other cases, it may be a source of contaminants as it gets released back into the water column. So if there's issues like that at a site, then we can account for that. So in terms of I mentioned the two models. HSPF has been around for quite a while. It's used worldwide, 20 plus years. And I mean, it actually is built off the old Stanford watershed model. So a lot of the formulations within the watershed model go back for decades. It's primarily been sponsored by the Environmental Protection Agency as well as the USGS. And over the years, it's continued to be refined and enhanced as more and more project work has been done. The HEC-RAS model is a 1D unsteady flow river model. More recent versions of HEC-RAS have now added 2D capability, but for the purposes of this demonstration study, we only use the 1D model. It has a very sophisticated sediment transport mobile bed modeling. It also has the capability of looking at bank failures. So in areas where, bank failures may be a significant source of sediment loading, it can account for that. We mentioned, with our, water quality submodels or submodules, it can do water temperature, it can do the water quality and contaminants. And it had 4 major version releases since 1995, and I think it's continually under development. It's used pretty widespread around the Corps and other agencies, and it's also used worldwide as well. So both of these models, have been used in many areas and are pretty widely accepted. So in terms of demonstration sites, we wanted to we picked 3 sites, and we wanted to pick sites in different parts of the country to kind of demonstrate, the utility of the modeling system within different climate zones, and also the different watersheds or different, military installations had different needs that they were looking at here. So the first site was Fort Hood, Texas. We looked at House Creek Watershed. The second demonstration site is Naval Base, Ventura County, California. And it resides within the Calle Creek Watershed in California there. And then we have demonstration site 3, primarily looking at Fort Meade, and it resides within the Patuxent River watershed. So a demonstration site 1, this is a relatively small watershed, 66 square miles or so. A lot of silty, clay loam type soil. It's pretty rural. It's basically used, I guess, to do a lot of training type activities within the area. So, and the major issue here was more sedimentation than it was necessarily contaminant. Water quality contaminant. So in terms of, the modeling we did, we basically set up the model, calibrated it for flow and sedimentation, and also started looking at some of the best management practices that Fort Hood was implementing in terms of gully plugs and contour ripping best management practices. And what we wanted to see is, number one, could we, basically calibrate the model to, let's say, conditions before they started implementing the BMPs. And then we wanted to implement the BMPs, and they've been collecting information since then, and see whether or not we're basically able to pick up or, basically replicate, what the reduction in sediment load is from that. So in terms of, calibration, we looked at some of the upland erosion type parameters, as well as some of the critical bed shear stress was calibrated in the final sediment reduction. And so some of the, just some of the takeaways from this particular site was that, we had sufficient flow data to, calibrate for the flows and so forth. One thing, I guess, a couple of issues in terms of the flows, that there was a wastewater plant that we had some information in terms of their releases at low flow, but a lot of that information was not in digital form. It was in just hard copy reports, and there was not as much. The fidelity of the information was not as good as it could have been, where we could actually capture some of the low flows coming in from the wastewater plant. One of the other issues that we ran into in terms of flow calibration with this site is that area has some karst features. So you do have some exfiltration that comes in from the streams during low flows, as well as you can have some channel transmission losses. As the flow goes downstream, it can lose flow due to some of these karst features. So those were a couple of areas that we identified that if you're trying to capture some of the low flow information, would need to be worked on, or maybe even look at a surface water or subsurface type model to kind of capture some of those the exfiltration and the transmission losses. The other thing that we took a look at is the USGS has a program called Lotus, and what this model does here is you can take observed storm and grab sediment samples, and then put that in and let the program develop a synthetic sediment, polluted graph. And then from there, the idea was, well, maybe we can use that synthetic to maybe compare against what we're competing with the model to see whether or not our statistics, were within acceptable ranges. What we found is there really was not enough storm and grab samples taken at this site or at within this watershed to develop, a synthetic hydrograph that was detailed enough to be able to do those statistics. So it was good enough for us to do graphical comparisons, which we felt pretty good about in terms of graphically comparing our sediment polluted graphs. But in terms of computing some of the statistics that we typically compute, it was not really good enough for that. So one of the recommendations is if that's something that an installation wants to have, be able to use the Lotus model, then they really needed to collect more storm and graph samples to get a wider variety of storms. All right, so the second demonstration site was the Calle Creek watershed in California. It's a little bit bigger, so it's 343 square miles. And here, looking at the land use, it's a nice mixture of high, from high density residential, commercial, industrial, all the way down to agricultural and so forth. So there was a nice mix of land uses to look at there, and the naval base obviously is down at the mouth of the watershed. There's a stakeholder group that is performing a joint TMDL study for the whole watershed. So, and they're looking at different contaminants and looking at who are the heavy polluters and what are some of the the BMPs or mitigation that can be done by the various entities or stakeholders within the watershed to try to reduce some of the concentration. One of the things here is that Calle Creek flows down through the Navy base down there, so they're interested in being able to quantify how much of the pollution that's leaving the base is due to military activities, and then how much is actually coming from upstream sources, and where in these upstream sources are the heavy polluters, and then trying to work with those stakeholders so that basically everybody kind of shares the load in terms of trying to mitigate some of these things. So here's just a snapshot of some of the output. In this particular case, we looked at total mercury, but we also looked at sediment. The same kind of information was presented in terms of sediment, total phosphorus, total nitrogen, total copper. And here you can see that you can from the modeling that we did, you can identify the areas where various constituents are coming from, and so the idea here is that you try to the ones that are heavily red, focus on those first, work with those stakeholders to try to reduce what's coming out of those areas. And then the hope is that, the overall watershed TMDL kind of comes back into compliance there. So, again, some of the conclusions that we came to from this demonstration site was, again, we have sufficient information to simulate flow, sediment, nutrient, contaminant results. There's been quite a bit of data collection that's gone on within this watershed over the years, so it lended itself pretty well to, I guess, validating the nutrient contaminant models that we had here. One thing that we know that we saw is that better mass loading of some of the constituents would improve some of the models. I mean, in some areas there was good information for developing our mass loadings, and then in other cases, more information would have been better. And then at basically at the mouth of the watershed, any BMPs that were implemented on the military base would not have necessarily benefited most of the watershed, but it does show the modeling does allow the DoD to look at their activities and how that compares to the other stakeholders above to try to zero in on some of these mitigation plans. And then our final demonstration site, we wanted to look at, so Fort Meade is in the upper part of the watershed, so this is sort of the opposite of what we had with Calle, and we wanted to look at, and also we wanted to look at something in the Chesapeake Bay area. This particular watershed is a little bit bigger, again, so 927 square miles. So we've kind of gradually moved up in terms of size. So we want to look at, the Northeast region in terms of climate. And here I'm just going to show a few results that we've gotten so far, that we have from the production. So stream flow, we're matching pretty well, and our statistics show pretty well with that. We've also had pretty good results in terms of computing our total phosphorus concentrations and loading. And we're running other constituents just for the sake of time. I'm just showing the phosphorus here. But what we're saying here is that we're sufficiently, for this site, we're simulating flow, sediment, nutrient, contaminant results. The interesting thing here is, so within the Chesapeake Bay, all of the people within the Bay have, I guess, TMDL goals that they are supposed to be trying to meet. And so Fort Meade has been developing some low impact development projects in an effort to try to reduce, I guess, water quality, sediment, and contaminants coming from the base. And we wanted to basically demonstrate that we could, account for some of those LID projects at Fort Meade, kind of show that, if you implement these or if you implement more, then they're meeting their DoD goals for that particular base to be in compliance with the total, the Chesapeake Bay's total TMDL there. So in terms of benefits of a system like this, it's basically a comprehensive assessment of the impact of the constituent fate and transport, both on and off the installation. So you can look at things not only on the installation, but also look at how things outside of the installation may be affecting the overall impact there. The other thing, we didn't really get into this, but HEC-RAS is used quite a bit by FEMA in terms of flood, looking at flooding, developing floodplain regions, as well as look at flood forecasting. So, from the standpoint of, so in addition, you could basically see where flood forecasting issues may be on installations with more advanced hydrodynamic modeling. Also, complex channel sedimentation can be accounted for, looking at how meeting, regulatory requirements and mitigation. And then also, the models can be used in varying climates there. So basically what we saw across all three sites was that, there's sufficient data being collected for flow and meteorological data. So we didn't really see a need to collect more of that information per se. There probably does need to be more sediment and water quality data collected if an installation really wants to take full advantage of a system like this. From a process standpoint, all of the models seem to, accurately or sufficiently model the various processes. The thing that we're seeing is that, if an installation wants to use this, probably installation personnel are going to be, pretty overworked, as well as they may not necessarily have the detailed technical ability to set up and run some of these models. So what we see is that probably DoD contractors are going to be more the people that actually set up and develop the models, and then they would need to make sure that information is put in a form that installation personnel, decision makers, could use that to make those decisions. And then just some of the things that the models can be used for would be like future land use changes, potentially climate change scenarios could be implemented, as well as looking at urban encroachment to the installations and how that might affect some of the installations. So I think that finishes what I was going to present today.
Wonderful. Thank you so much, Billy. And to our audience, this is a reminder to please submit your questions for Billy using the Q&A box that does appear on your screen. And if you could, when you submit your questions, if you would also put your organization or affiliation at the end, that would also be helpful. We have received a number of questions. The first one is, have you compared your Fort Meade model to the CAST or CAST models that the Chesapeake Bay program has developed?
We have not explicitly done that. I think we had in our last IPR, we discussed that might be something that we might want to possibly look at, but we have not explicitly compared those two.
Okay, thank you. You said mitigation for mercury at the base, and I think this was at the site in California, would not help the watershed, but would it help the receiving waters?
Right, yes. So yeah, it would help the receiving waters in terms of as it goes out into the ocean. I guess my point with that was, let's say like in the case of Fort Meade, which is at the upper part of the watershed, reductions in loading, or concentrations coming out of Fort Meade would improve water that's going down to downstream stakeholders. But with in the Calle Creek example, I was saying that any mitigation that was done at the site there, I mean, yes, it would be an improvement in terms of water quality going out into the ocean, but it doesn't really help any of the stakeholders upstream.
Okay, understood. Thank you. Along the same lines, within that watershed, could you discuss some of the issues related to the watershed load estimations in the Calle
Right.
watershed?
Yeah, sure. So some of the probably the biggest issue there is with the ag lands and the issue. So with the ag lands, we could get, let's say very general mass loadings, but there's an agreement, I guess, with some of the state entities there that collect that information, that they can't give out the mass loadings per farm or per ag, field. And so so we had general regions where we had an idea of what the mass loading was. We didn't have the finer spatial resolution in terms of where some of the mass loadings were. That information actually exists, but it was just an agreement that the farmers had with the agency there that would not be presented to the public.
Okay, thank you. Have you used these models to examine any fisheries or habitat issues?
These models are actually used, in those studies. And in fact, the HEC-RAS, well, in two cases. So the HEC-RAS model, the water temperature is being used on the Missouri River, where we're looking at changes in, reservoir operations, as well as looking at flows coming in from some of the power plants, looking at thermal issues in terms of fisheries as you move down through the Missouri River. We're also using it in the Columbia River, looking at water temperature for salmon fisheries up there, as well as, and I didn't mention it here, but we're actually doing some work with the Northwest Division to add a total dissolved gas capability into HEC-RAS, so that you can look at, TDG and look at how that might be affecting fish and how we can maybe change operations in the reservoirs to reduce TDG.
Okay, excellent. Billy, would you let us know the status of the HEC-RAS WQ or water quality release?
Sure. So we have a beta version that, like I've mentioned, we've been using for testing, validation, and even on some, select study partners. The full release, where if somebody wants to go to the HEC website and download it for their particular project, we're shooting for the May 2019 timeframe. And what the holdup has been is trying to get a lot of the GUI work finalized, as well as getting the final documentation such that our Hydrologic Engineer Center can actually make that final release and get it up on the website.
Okay, thank you. You mentioned using the models at other locations and for a variety of purposes, which you've also talked about here in the Q&A session. Can you describe in a general way what the minimum data set is to calibrate the models, some of the basic information?
Right. So some of the basic information would be precipitation data. And I would say you need sub-daily, hourly, 15 minutes to hourly precipitation. Meteorological data, to the tune of hourly data would be sufficient. In terms of, you need flow data. And again, sub-daily in order to, calibrate to flow quantity. Sediment, I think, if you had, sediment, graph samples and some storm samples, just to basically, make sure that your sediment computations are within the range of what you're seeing there, and you want to, collect that over a number of different frequency events. And then same thing with the water quality. In terms of, you need land use data. So, depending on whatever time frame that you're trying to run, you want to have representative land use. Soil texture information is relatively, easy to get from the USDA. Elevation data, typically we use 30-meter DEM, digital elevation maps, to develop some of these things. And then probably for the riverine, either have, survey channel cross sections, or if you have LIDAR, sometimes LIDAR information will be sufficient to be able to cut sufficient channel cross sections for that type of stuff.
Okay, thank you. Could you expand on to what extent climate can be incorporated into these models, and could sensitivity tests be performed with them, given the kind of more coarse resolution that climate projections typically require.
Right. So there would have to be, basically, when I say you can incorporate climate change scenarios, you can basically go in there and change your precipitation amounts and patterns, and as well as your meteorological, so change things like air temperature and so forth. So what I would see is somebody who is, let's say, maybe a climate change modeler would have to, take the information from those models and do some downscaling down to your watershed. And then you would work with them to take that information once it's been downscaled to incorporate into the models. And then, you would, and I know different climate models, produce different results. So you might need to, select a variety of them to look at, sensitivity to, variations in some of those results.
Okay, thank you. And we have time for one or two more questions. At Fort Meade, would you please discuss what types of BMPs are being evaluated?
Right. So some of the BMPs, sure. So some of the BMPs that they're implementing are things like pervious pavement. So the idea here is that, rather than having water just completely flowing off of a pavement area, there would be some infiltration. So some capture of the water as well as contaminants before it actually exits the parking lot. They have some bioswales where, again, what you want to do is slow the water down and allow it more time to infiltrate before maybe it reaches a storm pipe or storm sewer. I believe they're implementing some rain gardens where, basically as water comes off of a roof, rather than just piping it directly into a storm sewer, they would steer it into a rain garden where there again is some infiltration that takes place. And then once it exits out of that, it may go into a typical stormwater system. So the idea here is that what they want to do is with these low impact development BMPs is slow the water down, provide for infiltration, and so that the hope is that over time, that you're more, trying to mimic the more natural conditions rather than more of an urban type setting there.
Okay, thank you very much, Billy, for answering the questions and for your presentation. And as I mentioned earlier, Billy will return at the end of the webinar to address other questions. So if you have more for him, please indicate that in the Q&A box. And at this time, we'll move to our second presentation. And it's my pleasure for this to introduce Ms. Heidi Howard, a research agronomist for military lands within the Army's Engineer Research and Development Center at the Construction Engineering Research Laboratory. She's located in Champaign, Illinois. Heidi is the program lead for development of methodologies and algorithms for quantification of cumulative interactions of land management and military systems on training lands. This includes the development, validation, and implementation of stormwater and erosion control management designs, military vehicle impact models, and vehicle impact assessment and vegetation recovery. She is responsible for research on sustainable lands and ranges for military installations. She holds a bachelor's degree in biology from Western Illinois University and a master's degree in natural resource and environmental sciences from the University of Illinois. Heidi?
Thank you very much for this opportunity. We're excited to talk a little bit about what we have done. A real technical, sorry about this, but my arrows are not showing up for forwarding the screen.
Okay, no problem, Heidi. We'll take over forwarding them if you could just use the slide number.
Okay, next slide, 42. So we'll talk about the benefits to the DoD, how the project started real quick, what our objectives were, our modeling approaches, our demonstration sites, and how you can utilize the tools that were developed for your installations. Background on this is that Tetra Tech actually, with the U.S. Air Force, developed a simplified spreadsheet for estimating stormwater runoff And this whole project kind of coalesced into this demonstration and validation. Slide 43. So based off of the results from the project that initiated this, Tetra Tech and Searle basically wanted to demonstrate and validate what I'll call SMOT, Stormwater Modeling Optimization Tool, which is a component. There's two components to it. We wanted to go and really go and stress test this and make sure that it worked across multiple regions, climates, soil heterogeneity, etc. So we wanted to demonstrate and validate SMOT, make sure that what we were utilizing actually could determine BMP size differences and specifically appropriately identify the proper modeling approach for stormwater management. We stress test SMOT using, like I said earlier, multiple climate regimes, as well as the soil heterogeneity. From this, we wanted to validate recommendations by going through a full modeling approach at 2 sites, and then finally demonstrate simplified tool for DoD decision-making. The background on this, slide 43, please, or 44, I mean. The background on this is that design costs are based on BMP sizes. And at installations, we have a requirement through ESA 438 to meet pre-hydrologic conditions. From this, determining which modeling approach may significantly increase the overall cost of BMPs if it's not properly identified, and also the efforts related to modeling can be significantly different from, you know, anything from a design storm event to all the way up to continuous simulation with optimization. So to meet 438, ESA 438, stormwater runoff requirements, we need to meet those pre-hydrologic and hydraulic conditions for post-construction. In other words, whatever that footprint is prior to any retrofits at an installation, whether it's installing a new parking lot or actually tearing down and putting in a new building, they're required to meet the hydrologic H&H conditions prior to that retrofit or redevelopment. In order to do that, you have to utilize BMPs that are low impact development BMPs to capture and increase infiltration of the stormwater. Keep it on site versus going into a stormwater system and discharging into, you know, directly out. It's not allowed to, infiltration. And this is actually for areas that are in exceedance of 5,000 square feet. And like I said, it has to be for, it can be either for new development or a retrofit of an existing facility, like a parking lot, for example. Changing it from gravel over to asphalt is a good example of that. One of the things that is required from ESA 438 is that you have to, through the, whether you're going through the MILCON process or, you know, anything that's on the installation, you actually have to document and track and report those pre and post results. So that requires some type of modeling or calculations to determine your runoff, pre-construction and post-construction. With SMOT, you have that capability to do the reporting, and it also informs the end users on what modeling approach would be best considering your site conditions. And I think that's one of the biggest keys to this, is that it informs how, it informs that installation stormwater manager or environmental manager whether or not they should pay for a very quick and dirty design storm assessment or a much more complex labor-intensive modeling approach. Based on that, you get significant savings for not just the modeling efforts, but you also get, payback in having your BMPs be the right size for your facility and distribution of those BMPs, whether, it's one big, large, bioswell, or if it's a series of bioswells that are placed, more along the lines of prior to entering your construction site. Next slide, 45. So I kind of talked on this before. There's to meet ESA 438, you have to either use 3 modeling methods. The first one is 95th design storm event. That's a very simplified, quick and dirty, plug and chug type of, pretty much anybody can do this. It takes, standard data sets. It's fairly easy to determine. Well, then you get into a more complex modeling approach, such as continuous simulation. A good example of that is the SWIM model, which is EPA stormwater management model. And then there's what we call a very highly complex, much more labor intense continuous simulation with optimization. A good example of that is SUSTAIN model. The SUSTAIN is a system for urban stormwater treatment and analysis integration. And, there's a significant difference between all 3 of these modeling approaches in both cost and in relation to time, and as far as your overall design results, your outcomes based on these 3 modeling approaches. Next slide, please, 46. So our project approach and modeling selection, basically we did a demonstration of our model selection tool and SMOT to determine if it does the best modeling approach for DoD site conditions. We wanted to ensure that SMOT can evaluate ESA 438 compliance at the lowest cost possible. That not only includes BMP costs, but it actually includes, the labor and time associated with modeling. And then to do this, we had 2 phases. Phase 1, which was basically the model selection tool, or MST. With MST, we are determining the best approach to minimize cost to volume for compliance with ESA 438. And then phase 2 was assessing the suitability and rigor of SMOT to determine how well it fit, and demonstrated that at 2 sites to determine minimum cost volume compliance strategies. Next slide, 47. So this is our approach. Based on the model selection tool, you will get, you use national data sets for this. It's all easily obtained, Sergo data, digital elevation model, climate data from stream gauges that are national data sets, etc. There's some data requirements specifically to the precipitation that you have to do a little bit of modification and make sure that it's lined up. But when you put your watershed characteristics as well as your regulatory compliance needs into the MST, it will, for an area of interest, it will go and provide you recommendations for either the design storm, 95th percentile rainfall, continuous simulation, or continuous simulation with optimization. That then, after you identify which modeling approach goes through, you would then go and have BMP sizing tool, and that's SMOT. And then the results for this are your stormwater management plan. Next slide, 48. So our modeling approaches, basically like I said, we took the installation data set for this, and we have, based on this, we have mine went back. I'm sorry, we have, okay, go ahead and click it. It should go to the next one. I'm having some problems here. See what it is. Okay, hold on a minute. Okay, there we go. Sorry. So we have the model selection tool, MST. Utilize your basic installation data. And when you, next, you're gonna have to click the next slide and it'll come up with a graphic. Okay, so you have your analytical elements, which Stormy is basically a spreadsheet tool that was developed by the by Tetra Tech in the Air Force. And from this, it can determine optimization, runoff management, and filtration. So you also have your heterogeneity curve number that also goes into this if it's not a design storm or a continuous simulation. And that will go into your continuous simulation with optimization. Click again. Next slide. We're just going to have to do that.
And we're showing and seeing slide 50.
Okay. You're at slide 50 now?
Yes.
Sorry.
Is that right?
Yeah, that's fine. So this is the spreadsheet tool for optimization, runoff, and management and filtration. Can we try to go and give me back the controls on this? And based off of this, you know, you have, yeah, I'm sorry, it's not working again. So you can change it back. So we have the spreadsheet tool for the optimization that basically you look at it and you have precipitation events, project setup, etc. All of this is in the MST. And you provide this, you know, your area of the development for the watershed, you know, what type of pre and post pervious and impervious requirements you're going to have. And then you go and input in here and calculate. Go ahead and click next slide. It'll calculate the requirements. So we wanted to verify that this actually works. Slide 51, and that's where we come into MST. So we did this for a series of 45 installations. We did a whole series of simulations for different percentages of A, B, C, D infiltration groups for the soils. as well as precipitation and your climate factors, et cetera. And we put it through MST across the U.S., all over, with varying conditions, like I said. Those recommendations from the MST were then compared with the spreadsheet tool that we had already made for that. And so, next slide. We wanted to go and compare that to slide 52, to the conditions that you would find, or to the results that were provided by the spreadsheet tool, which basically is EPA tool. Can you click again, please? So for all of these simulations, we basically had an extremely strong correlation of fit. So 98% of the outputs actually were what came out of the MST when we did a simplified version of the modeling. So the MST was very accurate in its prediction. Of that, only 2% were of question. And those, as you can see, are the ones with where you have extremely high heterogeneity. And then when we had one where we had A-class soils, that there really wasn't a good match for that for some reason. We still haven't quite figured that out, but 98% is very good. Next slide, 53, please. So, based on this, and from the results of the MST, we looked at a whole series of installations, and we said, okay, we're going to go and take these through, and we're going to do 2 installations where we're going to do full-on hydraulic modeling approaches using continuous simulation and continuous simulation with optimization for an area of, or footprint of an area that could be redeveloped on an installation. And what we would do is we'd put it all through there, make sure that we verified that the MST actually did predict correctly, and that SMOT would then identify where the cost savings would be based on the modeling approach for the soil conditions and climate for those installations. Next slide, 54. Like I said, we did a full-on modeling approach for this using national data sets as well as some installation data sets, as you can see. And based on those modeling approaches, we'll get BMP identification. Next slide, 55. So these were some of the criteria that we had. You know, we wanted to go and look and see, is the MST actually recommending the correct modeling approach for the installation, for both installation 1 and 2? And is the cost savings potential between the modeling, continuous simulation only, and continuous simulation with optimization, is it going to be greater than 10%? So in other words, is it worth the effort of going, you know, between those 2 modeling approaches, because there's a significant labor cost and data requirement for between those 2 modeling platforms. So we looked at that. The other issue we wanted to look at is regulatory requirements. So both of the installations would be for ESA 438, of course, and one of the other installations would have a TMDL associated with that to see if we would still get that same cost factor. We also wanted to go and make sure that, you know, I said it a little earlier, but future development was critical for both of the installations, and data availability was the final item that we looked at when we were selecting our installations. So 56, please. So these are the installations that we basically were identified as either continuous simulation or continuous simulation with optimization from the MST with a cost savings of 10% or more. From these, we down selected to the two, Aberdeen Proving Ground and Naval Air Station, Key West. Next slide, please. So the data sets that we obtained from both of these installations they were identical, basically. You know, we needed to ensure that the area of interest had their storm drain utility network actually identified and mapped. So they had land use classification that could be developed, rainfall, availability of that, precipitation data, soils, if they had any existing BMPs that they were documented, as well as in a master plan, et cetera, that they had both impervious areas as well as pervious areas, that we could get a hold of their DM and inundation confidence. Next slide, 58. So these are the two sites. The development scenarios for both APG and Key West are the same. So we were looking at within an area, and you'll see here next, but we wanted to see if SMOT and MST actually worked, if it worked with a 30% versus a 60% versus a 90% development of a pervious area or area that hadn't really been developed prior to. From this, you can see over on the left that APG has very high heterogeneity with their soils. You know, they have B, C, and D soils across the installation, whereas over on the right, we have Key West, and they pretty much only had A and D soils. So it was either sand or it was high clay. Slide 59. So installation 1, APG, what we looked at was a area of interest on there. You can see it's identified. Click again. Based on that, we went and within this next area, we identified an area of interest. Click again. You can see up in the upper right, that's our area that we did a full-on modeling, both continuous simulation and continuous simulation with optimization. Click again, please. So we did it for the current development. Click again. I'm having a delay on my side, like a few minutes, second. Go ahead and click again. This is the 30% impervious. And then from that, we went to 60 and then 90. Just double click, please. And you can see where with the 30%, we have one big lump BMP down at the bottom of the drainage area. So that we could go and get it in there. Now, when you, the next one, you'll see the distribution across that drainage area. So your smaller BMPs, et cetera, are going on in there. So we then did, ran the SMOT, which is what you're seeing right now. Go ahead and click it. So you run that decision model, and sure enough, when you run that, it came out that for APG, it actually says continuous simulation only. So with that, you have a smaller size BMP, or not smaller size, but cost-wise, you have a BMP that is much less money because the soils that within there are just not, there's not enough heterogeneity to justify doing optimization. There's not enough cost difference there. Next slide, slide 61. So this is the results of that as far as the cost and the footprint. You can see there's really not that big of a difference between the two. You're talking, you know, size-wise, it's minimal with size, and then cost, it's you know, it's really not that big of a difference. Next slide. It's Key West. Key West, slide 62, sorry. Key West was the second installation, and if you remember there, with Key West, there's really only two soil types, A and D. Key West, it was identified that you needed continuous simulation with optimization. So looking at our area of interest, go ahead and click through. There's our area of interest that we have. And from that, we did our full-on hydrologic H&H modeling to determine whether or not continuous simulation versus continuous simulation with optimization would make a big difference in cost and size of the BMP proposed. And I should say that these are just infiltration basins. They're sediment basins. So go ahead and click again. In this, we have, you know, our BMPs are falling in both A and D soils. And cost-wise, we're looking at, there is a difference here, go ahead, between the two soil types. Go ahead and click again. Go ahead and click again. We looked at distributing that across the installation, and based on this, you know, the existing and post, the average annual flow volume was significantly different as far as cost. Click again. Go to slide 63. Okay, so running it through SMOT again, go ahead and click. We ran the decision model, and based on that, it came out with continuous simulation coupled with optimization is required, because the BMPs in continuous simulation, the soils were, you know, there was a cost difference in that. And so the soils are more heterogeneous, they have a higher heterogeneity, and optimization, when you add optimization in there, the results are actually significant in the cost savings and distribution. Next slide, 64. So this is the difference between those. as far as the BMP cost and how large of an area it is. Next slide, 65, please. And so what we did was, for both of these sites, we did scenarios, where we are, I'm summarizing basically what it is. So go ahead and click. Okay. Should be able to go and click 2 more times, I think. So with Aberdeen, basically we've got an area that MST identified that continuous simulation is the correct way for all 3 levels of development, or pervious, going from pervious to impervious soil conditions. So when you look at that, you have continuous simulation across there for both when you use the MST, as well as when we did the full-on hydrologic analysis. Next slide, 66. So this just summarizes what the design output is from MST, or I'm sorry, from SMOT. Basically, it gives you a generic, generalized, bioretention area, what size it is, and the depth and requirements for that. So this is one of the outputs that you would receive. Next slide, 67. And for now, what Tetra Tech and we are looking at, go ahead and click that, are different graphical GUIs for looking at how you can go and, use MST and SMOT for looking into how you can optimize areas and do individual stormwater solution, management development for it. Next slide, please, 68. Okay. Outside of all my technical difficulties, because of my need for animations, I apologize. MST, I hope you guys gleaned that. MST is actually very useful for determining an appropriate modeling approach for an installation. It does optimize BMP placement. You're going to see, the cutoff is about 10% size savings is what we used. You have the capability to do sizing, documentation, tracking. It's an Excel environment, so it's easy to utilize. You can get it and input it into, whatever Access database or, your GIS that you need, so that your results are integrated into your, whether it's a scope of work or BMP size, master plan, any type of compliance reporting that you may be required if you have a 303D or TMDL associated with your streams. And also it informs for just in general, it should be helpful to inform your statements of work or whatever you're developing. It should go in there and be able to go and give them a good idea as to, okay, well, this is justifiable, it makes sense, etc. As far as BMP planning tools, you do get conceptual design fact sheets and reports. Like I said, it helps with master planning. It also can help you greatly if you're in an area such as like the Chesapeake watershed, where you have to do tracking trading, BMP sizing, all of that reporting requirements. And then it prioritizes and selects, helps you select by ranked efficiency, effectiveness, and other benefits. Slide 69, please. These are some of the things that Tetra Tech has been working on, further development. They're working with the Air Force on that. So this is how they've integrated into a reporting process for an Air Force base. And you can see for this that there's a lot to be had for it as far as just master planning and decision making. Next slide, 70, please. So our results, conclusions for phase 1, we had really good correlation with MST. And we found out that both MST and SMOT work across varying climates and soil heterogeneity, which was what our goal was. Phase 2 for the full hydrologic modeling, when compared to full-on modeling efforts with continuous simulation and continuous simulation with optimization, the MST and SMOT outputs were correctly identified through the cheapest modeling approach for both sites. So the correlation was there. Next slide. And that pretty much wraps up the talk. Thank you for your time.
Okay, wonderful. Thanks, Heidi. And if I could remind our audience at this time, if they have any questions for Heidi, please do submit them using the Q&A selection that should appear on your screen. And we do have a couple questions, Heidi, for you. The first is, when are MST and SMOT available for release?
We can send out the spreadsheet for it right away if you need. You just email myself and I will distribute it. We're in the process of putting it into we've already put it into Net Zero Planner or Simple, which is a Corps of Engineers platform. It has gone from being only a restricted platform for .mil, and the server was just recently changed. So we're anticipating that the release will be here within the next month or so. Oh, and I also need to mention that we have YouTube tutorials, etc. So spreadsheet is available right now.
Excellent. And so what level of expertise in general is needed to use these?
One thing, I think the most informative information when we distributed this out to a high level of or varying level of capabilities was that you actually do have to have a good foundation for H&H. So, a general engineer, a civil agriculture, someone with a good soil water background should be able to go and do this with no problem. So your stormwater managers on an installation should be able to go and effectively use it. The districts definitely can use it.
Okay, great. At this time, we'd like to bring Billy back for one or two just slightly more general questions for our two speakers today. And the first question is, are there other ERDC developed tools for watersheds or stormwater that could be useful to installations that you'd like to discuss today? Billy, is there one or two that you would like to mention?
Sure. So on the watershed side, we do have our coastal and hydraulics lab we've been working with in terms of a grid-based watershed model called Geisha. So it's a surface, subsurface model. So as I mentioned with Fort Hood, where you have the karst issues there, a model like that would be able to account for, the exfiltration as well as channel transmission losses that you would see there. So that's a more sophisticated model than HSPF in terms of setup and running and so forth. And it's a more physically based model, but it would probably be more applicable, from the hydrologic standpoint there. On the surface hydrodynamic side, if you're in it, let's say like in a case like Callegas Creek, or maybe even the case with Fort Meade, where you're looking at maybe things down towards the lower part of the watershed and you want to get into maybe an estuarine area. We have been working with, again, our coastal and hydraulics lab on the adaptive hydraulic model, which is a finite element based surface water hydrodynamic model where we've implemented our nutrient contaminant simulation modules into that. So if an installation needed to have, multidimensional modeling, for the surface water, then that would be another tool that could be used.
Okay, great. And Heidi, do you have one or two to mention?
Can you repeat the question?
Sure. So, any other tools that were developed by ERDC that might be useful for stormwater or BMP design or planning?
Well, I think ERDC has developed a number of, Billy actually did it, which was the low impact development, a 95th percentile tool that is spreadsheet based also, that can do your calculations for an installation that they can use. We're always trying to improve our low impact development guidance. We have a number of technical reports and public works technical bulletins that identify a number of LIDs technologies and testing and determination of how effective they are on installations, specifically in areas that are much more different than what they initially were designed for. So those can all be obtained through our just Googling ERDC and LID.
Excellent. Thank you. So at this time, we've reached the end of the webinar. We'd like to thank again both of our speakers, Heidi and Billy, for the very informative and interesting presentations and for addressing the questions from the audience. Our next webinar in this series is on November 15th, and it is on a related topic on stormwater impacts on sediment recontamination. It will feature Mr. Michael Pound from the Naval Facilities Engineering Command Southwest and Dr. Danny Reibel from Texas Tech University. Registration is open for that webinar, so please visit the CERTIP NESTCP webinar webpage to register for this one and other webinars. And before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on the webinar webpage in case you would like to refer to them in the future. And we would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.
Thanks.